Predicting how well a machine learning model will perform given a certain amount of training data, its learning curve, is crucial for efficient model development. Ideally, we want to know this before investing time and resources into training. Traditionally, this requires extensive experimentation, training models on varying dataset sizes and observing the test error. This is computationally expensive, especially for large datasets and complex models. Current theory often relies on simplified data distributions or asymptotic analysis, which may not accurately reflect real-world scenarios. The key insight of this paper is that the eigenfunctions of kernel operators, which govern the behavior of kernel regression, can be well approximated by Hermite polynomials of the data. Essentially, the paper proposes the Hermite eigenstructure ansatz, or HEA, as a reasonable approximation. This is profound because Hermite polynomials form a complete, orthogonal basis and are linked to the data's underlying distribution. The paper provides analytical proof that this holds true for Gaussian data. Surprisingly, even for non-Gaussian real-world image datasets, the HEA turns out to be a good approximation. The method works by first estimating the empirical data covariance matrix. This captures the anisotropic structure of the data. Next, it decomposes the target function, the function the model is trying to learn, into a polynomial basis. Using the HEA, these two pieces of information, data covariance and target function decomposition, are sufficient to approximate the kernel's eigenstructure. Specifically, it analytically approximates the eigenvalues and eigenfunctions of the kernel integral operator. With an estimate of the eigenspectrum, the paper leverages standard kernel regression theory to predict the learning curve, test risk as a function of sample size, without actually training the kernel regression model. It also establishes a fascinating connection to how MLPs learn. Early layers learn low-order Hermite polynomials, progressing to higher-order polynomials in later layers, mirroring the order predicted by the HEA. The paper demonstrates impressive results, accurately predicting learning curves on real image datasets like CIFAR 5M, SVHN, and ImageNet. Importantly, this method avoids the computational bottleneck of directly constructing and diagonalizing the kernel matrix. This work is a proof of concept for a more general, end-to-end theory of learning. It connects the statistical properties of the data, the structure of the model, in this case, kernel regression and MLPs, and the resulting model performance. It offers a promising avenue for understanding and predicting the behavior of learning algorithms on real-world datasets before expensive training.